Here's a solution to the last problem from the online homework for section 7.3 and 7.4, where we see an application of trig substitution to finding the area of a geometric figure. And this is just a generalization of what we did with finding the area of a circle. But in this case, the problem is given with general parameters a and b that we need to keep in the problem through the whole thing, so rather than specific numbers. So when you have something like this, it's probably a good idea, if you're not really sure about all the a's and b's, is just to try the problem using actual numbers like and use kind of strange numbers like a equals 5 and b equals 3 or something like that, and just try working through it with numbers in it to see what's happening. And the idea is that you should be able to do all the same steps using parameters a and b, where you just treat them as constant numbers at the appropriate times, but you just don't happen to know what the appropriate numbers are. One advantage to using kind of odd numbers like 5 and 3 or 7, and not odd, like not even, but like unusual numbers, not like 2 and 4, is that because they're not divisible, you won't be tempted to do a bunch of arithmetic. And then in the end, you can see where the 3's and 5's are in your final answer, and that's where the a's and b's should be when you do it more generally. But I'll just go ahead and do it in general, since we did an example like this with a circle with numbers. That'll be the most like the specific version. So in this case, we see the a squared minus x squared under the square root sign. Oh, I guess I should set up the integral first. We're trying to find the area of the ellipse. And so the area of under this curve, starting at negative a, going to positive a, that will be half of the ellipse. And so if we double that answer at the end, then we'll have the area of the whole ellipse. So because they're only letting us write in a box here inside the integral, we could just double the integrand in the first place. So if I put in twice the formula for the ellipse, then that'll work as the integral. The other way to think about it is you could think of it as the area between two curves where the bottom curve is just the negative of the top curve. And so you could think of it as a subtraction between the top curve minus the bottom curve, which is also effectively doubling that formula. So that's what goes there. Because we have a squared minus x squared in the integrand, that means that a substitution x equals a sine of t, or sine of, I guess they're going to use theta, a sine of theta will result in dx being a cosine of theta d theta. And so I can make this substitution into my integrand as the square root of a squared minus a squared sine squared. So don't forget, if x is a sine theta, then x squared is a squared sine squared. You're squaring everything. And then times a cosine theta d theta. I'm just not giving myself enough room here, am I? All right, hang on. That's magic. I can get rid of this. Then the trig identity that's going to be used, of course, is the one that we keep using. So 1 minus sine squared theta equals cosine squared theta, which means if I multiply that identity by a squared, then a squared minus a squared sine squared theta is a squared cosine squared theta. And the left-hand side of this is what's under my square root sign here. So I can change this to be the integral of the square root of a squared cosine squared times a cosine theta d theta, and if I have the a squared cosine squared under the square root sign. As long as I know that a times cosine is positive, then I can just remove the square root sign and take the square root. So we move that up, we move that over, give myself a little more room. So at this point, since I'm thinking about whether the thing under the square root sign is positive or negative before it gets squared, it's worth looking at the limits of integration. The original limits of integration were negative a to a, and so in my integral, I really would like to convert those to be in terms of theta. So if I go back to the substitution here, then I can actually give some thought to the two cases. When is x equals a, so in other words, when is a sine theta equals a, and that will happen when theta is pi over 2. And I could also ask, when is x equal negative a, so that's saying when is negative a equal to a sine theta, and that will happen when theta is negative pi over 2. So my limits of integration, instead of going from negative a to a as a range of x values, I can go from negative pi over 2 to pi over 2 in terms of theta. And so at that point, I know that the cosine function, when theta is between negative pi over 2 and pi over 2, the cosine function is always positive. So I'm not going to have to deal with any kind of absolute value or anything when I take the square root of the square here. So finally, I'll have minus pi over 2 to pi over 2. The square root of the square is just going to be a cosine theta, and then there's going to be another a cosine theta. So altogether, I'll have a squared cosine squared theta d theta. So that is the transformed trigonometric integral, whose answer is going to be my area of the ellipse. I feel like I lost oh yeah, I did. I lost the 2b over a. I'm sorry. Right? I got so focused on the trig identity, I lost track of the rest of it. I have not brought this along with me at all, so I want to make sure that is sitting out here the whole time. So it would make sense for the a squared inside the integrand to also go up there. So maybe I'll write one more step here before I go to the next page. So if I bring the a squared inside the integral outside, I'll have, if I do it correctly, I'll have 2ab outside the integral, then cosine squared theta d theta. And that's going from minus pi over 2 to pi over 2. All right, so that is my integral completely in terms of theta, and the result of that integral will be the area of the ellipse. So go to the next page. The homework problem makes you actually fill in this thing as you go, so it makes you choose your x, choose your dx, all that sort of stuff. So hopefully all that follows fine from what I did on the last page. But what I need to do here is actually evaluate the integral cosine squared theta d theta from minus pi over 2 to pi over 2. So remember, and this is where we got to with the one for the circle in class, that makes sense that ultimately the actual integral would have something to do with that same problem. But the other thing you'll notice here is that the a and b parameters aren't present here at all. The result of having just the general a and general b, all of that just produced that 2 times ab term that we pulled out in front. So what's left has no parameters in it at all, which is kind of nice. Anyway, so to do this problem, this is the one where we, in our crib notes, we might have a note about the cosine of double angle. And I don't remember formulas very well, so I'm happy that I can remember that one. The reason we use that is because I can solve that equation for cosine squared. So I can take that double angle formula that I feel comfortable with, and I can add, let me just make that a more clear theta. I could take that double angle formula up here. I can add 1 to both sides and then multiply both sides by a half. So multiply both sides by half after adding 1 to both sides. That will give me 1/2 1 plus cosine 2 theta. And that's still minus pi over 2 to pi over 2. And that, in turn, is just 1/2 theta plus 1/2 sine 2 theta, evaluated from minus pi over 2 to pi over 2. And that's a pretty easy antiderivative, cosine of 2 theta. You can use a substitution there, but we've seen many times what happens when you have this constant times your variable, that just produces the reciprocal of the constant out in front. So to me, it's easier to write this down and just think a second about, is this really the right way around? The derivative of theta is 1. The derivative of 1/2 sine 2 theta is positive cosine 2 theta. So if I think of the derivative of this as this, I feel pretty good about that. And so then finally, when I plug the numbers in, I'll have theta's pi over 2, and then this guy here is not going to do anything interesting at all, because sine of pi and sine of negative pi are both 0. So when you put pi over 2 in for theta or negative pi over 2 for theta, this is going to be 0. So you end up with 1/2 pi over 2 plus 0 minus 1/2 negative pi over 2 plus 0. And so that's 1/4 pi over 2 plus 1/4 pi over 2, which is pi over 4. So that is that's the integral and of cosine squared. And no, that's pi over 2. Sorry, I lost track of something. It's pi over 4 plus pi over 4. Sorry, I knew that wasn't right, but I couldn't see what I did wrong. Anyway, pi over 4 plus pi over 4 is pi over 2. So remember, on the previous page, we had that the area was 2ab times pi over 2. I'm sorry, 2ab times the integral, and then the integral is pi over 2. So the final answer for the area of the ellipse is the 2ab part times the value of the integral, and so you end up with just ab pi as the area of an ellipse. And just to make sure that makes sense to you, remember that a circle is just an ellipse with both the major and minor axes equal. So if A and B are both r in that picture, then you have a circle with radius r, and the formula says r times pi, which is pi r squared. So that is consistent with what we know happens with a circle, but before an ellipse, it's just basically it's being scaled. Okay, that's it.